Okay, it's really a great pleasure for me to introduce our next speaker, Renata Wentzcovitch. Renata received her bachelor's master training in physics at the University of São Paulo in Brazil. And from there, she moved to Berkeley for her PhD in physics. With her degree in hand, she first went to Stony Brook for a postdoc in the physics department. I actually pretty sure I met Renata then, but she was a physicist and I was a geologist. So we didn't see such a common pathway at that point. But then Renata went on to Great Britain, where she spent a lot of time in the Department of Geological Sciences of University College London with David Price and his group, as well as in other institutions in London and in England. And I think that probably was where the light came on as to how much earth science needs someone in her profession. From that point, she was a professor at University of Minnesota in the Department of Chemical Engineering and Material Science. And recently in 2017, Renata moved to Columbia University as professor of applied physics and applied mathematics, in addition to a professor of earth and environmental sciences and member of the Mont Doherty Earth Observatory. And that's where she is now. She was the founding director of the V-Lab, the virtual laboratory for earth and planetary materials that had a lot of educational outreach and a lot of science produced on materials of earth materials. Has been numerous fellows of numerous scientific organizations from physics to earth science. Received the Humboldt Award in, 2008. Renata's research is devoted to computation, quantum mechanical studies of materials at extreme condition. She applies and develops material simulation methods to study the material properties at high pressures and temperatures. And this is sort of important to me, that back when I was a graduate student, I was looking at the various ways that you could calculate elastic properties and so forth. And MGR, make a model that describes SiO2, and then take those two models and put them together, and you'd be totally wrong in defining the properties of olivine or pyroxene or so forth. And so theory in terms of predicting properties at that time just didn't seem to work. And the physics that has come along since then has made such a great improvement in that it offers us the ability, compared to a laboratory measurement. You want to measure elastic constants at some pressure and some temperature. It's a great effort, and now you want a new temperature, you want to slightly change the composition, you have to go back to scratch. Well, with computational methods, you're not limited in pressure or temperature or composition, and it offers a real great input into the earth science studies of the mantle and the core and so forth. And her current research interest has been applied to doing mineral physics or modeling the mantle, seismology, and geochemistry, looking at exoplanets and what conditions there might bring, properties of strongly correlated oxides and crystal defect spin transitions has been a place where she's contributed an enormous amount to understand how they might affect the properties and to compare predictions with the results of experiments. Well, so there's so much that Renata has given to us, and today she will add to that her talk. And so I welcome Renata speaking on the computational mineral physics challenges and opportunities ahead. That's yours, Renata.
Okay, thank you very much, Don. Thank you for the invitation. It's a real honor to be here. So let me start sharing my screen. Okay, my talk is about computational mineral physics, challenges and opportunities in our field. So much has been done and achieved in the last 20 years, at least 20, 30 years. My involvement with earth science seems to have been fate. I did my PhD in high pressure, studying materials, semiconductors at high pressures, and eventually I made my way to earth science that has the greatest problems on the earth in material simulations, I believe. So my talk, I'm going to give an overview, which is basically a retrospective pointing out the breakthroughs, the techniques that have contributed, where they need improvement or they have improved, and the challenges and opportunities that we have in our hands today. Of course, this is a broad field. There is a community that has increased considerably, and I really cannot cover, but I will cover some major breakthroughs in this field. And then I will talk a little bit about infrastructure, that I think it's something very important that is pointed in the Earth in Time report as well. As an overview, material simulation in earth science, mineral physics, is an established field of research today. And we are great partners with experimental mineral physics. Simulations have approximations, and reliable measurements can point us to areas that need improvement and validate our methods. And then with building, we build confidence and reciprocate the benefit to computational, to experimental measurements. So it's a very integrated field that experiment and computations, they grow, they evolve together. We are great partners here. Of course, we partner also with seismology and geodynamics. We calculate the densities and velocities that today are used to interpret seismic velocities in the mantle. And we offer thermodynamic properties that are used in geodynamic simulations. The standard modeling techniques in this field, they are based on density functional theory. There are approximations in dealing with the electron-electron interaction, and the standard ones, popular ones, you heard well about them, and the local density approximation, LDA, generalized gradient approximation. There are meta GGAs now that are becoming very prominent in this field, in addition to the local density of the electron and the density gradient. We also include the kinetic energy density in these functionals. And hybrid functionals also improve the correlation energy and by introducing some portion of Hartree-Fock. Of course, the popularity of these methods decreases to the right because the computational cost increases to the right. For strongly correlated materials where the one electron theory of these functionals above does not apply, we have DFT plus U, which has been very popular and successful. DFT plus DMFT, which is much more costly, and but also offers some benefits. Quantum Monte Carlo also. So also they are this more accurate and computationally costly are less popular methods. Codes are, there are many codes available. We all know them, and they are highly accessible and trustworthy. Thermodynamic and thermoelastic properties calculations of free energies of function of pressure, temperature, and strength, the calculations of ab initio first principles phonon, DFT phonons, and the quasi-harmonic approximations that assumes that phonons don't interact with each other has been very successful. They allow us to reach the thermodynamic limit as long as the phonons are harmonic. Molecular dynamics and thermodynamic integration is also very useful, but it happens that these simulations cannot have more than, cannot be easily conducted with more than hundreds of atoms. And classical force fields are still very desirable for molecular dynamic simulations. This is where we have one of the greatest opportunities we have today in this field. Infinite opportunities, I would say, with machine learning, neural network potentials. Simulations with ab initio accuracy containing, having hundreds of millions of atoms have been performed. And this is something that funding agencies are very keen to fund. So this is an area that it is still very exploratory, but it's a great opportunity. And of course, we've seen since 2004, the introduction of materials discovered methods based on genetic algorithms, random search, etc. So let me remind of what we've accomplished regarding the lower mantle. These are the main phases of the lower mantle. Perovskite, post-perovskite with complex, perovskite and post-perovskite with complex chemistry, ferropericlase, which celebrated by its spin transition, calcium silicate perovskite, a complex phase that it still challenges us, but we're making great progress in studying them. So regarding 2004 was a year that we learned a lot about methods. And it's because of the discovery of post-perovskite transition in a diamond anvil cell at 120 GPa and 2500 Kelvin. We received the X-ray diffraction from Japan and started working and searching for this phase. And by random search and starting from possible crystal structures, we identified this phase that was thermodynamically stable at high pressures and temperatures. And this was the phase boundary that we calculated using different functionals, and it displayed for the first time the accuracy or inaccuracy of DFT in predicting phase boundaries or difference in energy between phases. This was a remarkable success that pointed right away to the uncertainty of these calculations. Which are still there. But what was really remarkable was the prediction of velocity discontinuity across this phase transition. At low temperatures, the phase transition occurs at lower pressures, and that's where there's a better chance to see this phase transition in the mantle. And this is the discontinuity in shear and compressional velocities. Relatively, the discontinuity in shear velocity is larger than compressional velocities, pointing to an anticorrelation between the change in Book modules and change in shear modules. And remarkably, our thermoelasticity methods based on quasi-harmonic approximation reproduced these velocities discontinuities. Of course, we had a great deal of uncertainty. This is the discontinuity across the phase boundary. And this is the uncertainty because of the uncertainty in the phase boundary itself. But there is a great deal of correlation of reproducibility here. Delta VS 2%, in the mantle 1.7% in a cold region beneath the Caribbean, where we expect to see this transition. Delta VP 0.5% in the mantle, 0.75%. So this was very surprising and rewarding and puzzling. The lower mantle is certainly much more complicated than the simple transition we investigated, but this feature must be robust. And that's why we're being able to reproduce. But there must be also some fortuitous agreement here. For some wrong reason, we are agreeing with respect to transition pressures, etc. Because today we investigate the same phase transition in alloys. ferrous iron and bridgmanite with ferrous iron and ferric iron, or just aluminum couple substitution, or aluminum and iron at the same time. And what we see as in experiments, that ferrous iron decreases the transition pressure, but also opens a two-phase stability field. Ferric iron pushes a little higher the transition pressure and has quite narrow two-phase region. So is aluminum, the aluminum bearing phase at the conditions of the mantle, and the iron aluminum coupled substitution. So here is a very interesting result that ferric iron and ferrous iron have very different effects on the post-perovskite transition. And this was clearly observed by Katalin, Sheen, and collaborators. And it's quite rewarding for us to see that the narrow region observed experimentally is clearly reproduced computationally. So there is an opportunity that if we investigate the nature of these discontinuities in the D double prime, we might be able to identify regions that are ferric or ferrous iron rich. For example, according to these calculations, a double crossing of the post-perovskite boundary is almost impossible in ferrous iron rich bridgmanite, but it's clear it can happen in ferric iron rich bridgmanite. So this is an opportunity, but the challenge in investigating velocities really reproduce velocities in thermodynamic equilibrium in an aggregate. This is the real challenge because these are strongly correlated systems. So ferropericlase, it's celebrated for its spin transition. Ferrous iron, 6 d electron, 5 electrons spin up, 1 electron spin down in the d orbitals, and you have a high spin and low pressure. The crystal field splitting actually increases the energy distance between the triplet and the doublet, and we end up with 3 electron spin up and 3 electron spin down at high pressure. This is the spin transition, and also occurs in ferric iron. But here is the blue is the compression curve in high spin state in ferropericlase with 18.75% iron, and red is low spin. And when we compare to the experimental data, what we saw really is a region in which the data crosses from the high spin prediction to the low spin prediction, and this is certainly a region with where both spin states are present. This is the mixed spin region. The compressibility increases in this region, and the book modulus decreases in this region. This region of mixed spin state broadens and shifts to higher pressure with increasing temperature. And although we have predictions that at low temperatures are in good agreement with the experiment, you will see what it is today, a little bit of tweaking, but it does agree well with experiments. But the challenge now is to go beyond the ideal solid solution models that we have been using, not magnesium iron, but high spin, low spin solid solution. Non-ideality of these solutions broaden these transitions. And this is still a challenge that we are facing right now. We needed to understand this spin transition better. Others have already pointed out a long time ago that this is the case. But nevertheless, longitudinal and shear compressional and shear velocities are predicted quite well at 300 Kelvin after tweaking a little bit with the energy difference between the high spin and low spin state. But this is what we really needed to address the mantle more carefully here. Brillouin scattering and ab initio quasi-harmonic thermoelasticity agree pretty well in predictions at 300 Kelvin. The same thing happens, of course, to understand the mantle, we still need to understand spin transition in the main system. Bridgmanite, there is no spin transition in ferrous iron in bridgmanite. There is a spin transition in ferric iron in the octahedral site. And it's a slightly higher pressure, but qualitatively the effect is the same. In the A site, no spin transition in ferric iron either. Post-perovskite, the same. The large site, no spin transition in ferrous or ferric iron, spin transition only in ferric iron in the small octahedral site. Aluminum is a poison for the spin transition. Aluminum kicks iron out of the octahedral site, and no spin transition. For us, it's a blessing because it makes easier in many respects, calculations of velocities and analysis of the lower mantle. But that's not the end of the story, of course. So here is a prediction of, so essentially, is this this softening of the book modulus that we see observed in the mantle? Well, this is a complex question, and one way to address this is to look at velocity heterogeneities, because this spin transition has a remarkable effect on heterogeneities. If you are a 75 GPa and you plotted the book modulus of the pyrolite aggregate as a function of temperature, what you see is that when you go across the spin, the mixed spin state, the book modulus softens, and the shear modulus doesn't change very much. So there is a region in the mantle where you have an anticorrelation between decay dt and the GDT. They go in different directions, and that has a remarkable effect in a region of the mantle that is isochemical. For example, in a pyrolytic aggregate, if it's a uniform region of the mantle, thermal anomaly coming from the core mantle boundary to the surface, for example, a plume, can be clearly seen, should be clearly seen in an S model, but the velocity is going to be disrupted in this region of the mantle because book mod BP is disrupted because book modulus and shear modulus go in different direction, and VP becomes less sensitive to lateral temperature variations. This is a feature that is seen in some plumes in the mantle, but is it really seen in the mantle? So here there is an opportunity. There are predictions. There are some reasonably there are some predicted velocities with predictive accuracy, with useful accuracy, and that we can be used to analyze velocities in the mantle. There are several groups using this type of calculated velocity, ab initio velocity, to analyze the mantle. And this is an area that is pretty blooming pretty much today. Can we see spin transition in the mantle? Well, one-dimensional models, unfortunately not in PREM, but perhaps it can be seen in AK 135. Brian Kinnett claims that he has seen signatures of the spin transition in this one-dimensional model. But we predict that you can see this in tomographic models. We decided to team up with seismologists and other colleagues in the field to analyze heterogeneities in the mantle. My colleagues analyzed 4 S models and 4 P models. And these models, at a certain depth, they have different velocity heterogeneity distributions. And but at different magnitudes, different center of these velocity distributions. So they made an effort to normalize these distributions and align them and use the common features in order to ask the question, point-wise, how many at a certain depth, and point-wise, how many of these models have delta V larger than 1 sigma, for example? How many models agree that this is a fast region or a slow region, delta V is smaller than -1 sigma? And so this is what they call the volt map. They count pointwise in the mantle the number of models that have large or large heterogeneities, positive or negative. And this is what you're seeing here. These are the cross sections of these mantle regions. And these are our volt maps. The dark regions are regions where 4 models agree that this is a fast region or there is a slow region in the S models here. Of course, this is not heterogeneity itself, but the heterogeneity is robust. And it's a common feature among all the methods, then this must be real. This must be a real feature. And here you see the vote maps for S models and the vote map in P models. If the velocities heterogeneity is not large, or there is no agreement between the models, then you see zero agreement, white regions. And there is a much greater agreement between fast and slow regions in S models than in P models, suggesting that, the disruption in compressional velocities is a real thing. It's real, and the trends we observe are what we expect produced by the spin transition, spin crossover in ferropericlase. I would like to say that in perovskite, if there is a spin transition in ferric iron perovskite, qualitatively has the same effect, even though we did not include ferric iron in this model, in the compositional models, only ferropericlase. But if it happened in ferric iron, it would enhance the effect of the spin transition in ferropericlase. What about calcium silicate is still a challenge for everyone. It's a highly anharmonic phase. Anharmonicity means deviations of the potential energy surface for atomic motion from quadratic. This leads to, in the quasi-harmonic approximation, phonons will interact with each other, but in anharmonic potentials, there is an interaction. Phonons, frequencies have a temperature dependence, and they have a lifetime. Phonons interact, they scatter from each other, and they have a lifetime. The way to study this problem is usually molecular dynamics. The probes, the anharmonicity of the potential energy surface. So this method, called the phonon quasiparticles, it probes the energy surface with molecular dynamics. The velocities, this extended velocity of the ions is projected on normal modes, and then we calculate the velocity autocorrelation function for this mode projected velocities, the BAFs, velocity autocorrelation functions. These BAFs, they look like that. They are an oscillating decaying function, and the period of the oscillation gives the frequency of this quasi-particle, this phonon, and the decay of exponential decay gives the lifetime of these phonons. In an MD simulation, we sample only few modes, a limited number of wave numbers, and we computed this quasi-particle properties only for these phonons sampled in the MD, but then we needed to extend and obtain the entire phonon dispersion. And we used the same technique that we used to draw phonon dispersions in harmonic phonons. For example, here, if we have at 0 Kelvin, calcium silicate is unstable. There are instabilities, imaginary phonon frequencies at some points of the Brillouin zone, but with increasing temperature, these phonons is stabilized. This is what is very important for us. So the phonon frequencies at high temperatures, the phonons the quasi-particles are stable, and we can use the quasi-particle properties also to obtain thermal conductivity. This is a little tricky. For example, if you have a lifetime of phonons and velocities, group velocities of these phonons that we obtain once we obtain the dispersions and the phonon specific heat, we can calculate thermal conductivity within linearized Boltzmann transport equation. And this is what we see here. Of course, lifetime for harmonic phonons is essentially infinite. We usually expect thermal conductivity to be larger or smaller for anharmonic phonons, for anharmonic systems, especially systems such as calcium silicates, highly anharmonic. But what's surprising for us is that the thermal conductivity of calcium silicate is 2.5 times larger of that of magnesium silicate. Yes, the lifetimes are smaller, but the velocities are considerably larger. And this has to do with the symmetry of the system. The symmetry of calcium silicate is larger Brillouin zones, In low symmetry system, the Brillouin zone folds leading to zero velocity phonons at the zone edge, and that drops the velocity, the average velocity of a system of lower symmetry. So the higher symmetry of calcium silicate leads to considerably large thermal conductivity. And it's a very surprising result, and we asked our colleagues in Japan, Ota Hirose, to measure thermal conductivity using post-light heating thermal reflectance, and they measured at 300 Kelvin, a couple of points at high pressure, and at 2000 Kelvin as well. And the agreement seems to be quite outstanding, better than we expected to achieve. But so here, what is the effect for the mantle? Well, calcium silicate is not a very abundant phase, but it can contribute to an increase in thermal conductivity of pyrrolite by 10%. But in MORB, where it's abundant, it could increase the thermal conductivity of up to 40%, which is going to be a very important piece of information to understand heat conduction across the core mantle boundary, where MORB crust is expected, it tends to accumulate. So here is a great challenge for us now, is to really predict thermal conductivity in solid solutions. Great challenge here. Beyond the Earth, how much time I have? Okay, I will go very fast. I promise that this is relevant for diamond and cell pressures today. So discovery of a super Earth type planet stimulated us to ask this question: what happens after post-perovskite? 10 years of research lead to this phase diagram that I'm showing here to you. Post-perovskite decomposes into an iron, where's my arrow here? Post-perovskite decomposes into a magnesium rich and a magnesium in a poor phase. And then the magnesium poor phase exalts silica, and you're left only with the magnesium rich phase, which finally decomposes into the elementary oxides at around 30 megabar. In the presence of magnesium, you don't have the magnesium poor phase, only the magnesium rich phase. And in the presence of silica, you have first only the magnesium poor phase, and then it proceeds to evolve in silica, etc. So these are predictions that have already been used to try to model the internal structure of super Earth. But these phases are very interesting, and the first one, the magnesium poor phase, was found essentially by brute force, by looking at all that is possible and stabilizing phonons that were unstable, etc. The magnesium-rich phase was more complex and was found using the adaptive genetic algorithm. Very interesting phase where all cations are in the same kind of site, which is coordinated, not cubic, but it's eightfold coordinated. Why these pressures are very high, but they are reliable. There are good low pressure analogs in which predictions and measurements have been made already. Magnesium germanate is a famous one. The first transition happens at around 170 GPa. Sodium magnesium fluoride, even better. They are not ideal or perfect low pressure analogs. Sodium magnesium fluoride or neighborite low pressure, right, display only the magnesium poor type phase. And this is predicted. This was measured. All these phases have been measured, have been found experimentally. The pressures are quite low here. Interestingly, recombination or decomposition transitions, they are hard to happen. I mean, high hysteresis, but and some metastable polymorphic transitions can be observed as well. So here, what is the latest predictions and measurements are on the magnesium germanate phase, the magnesium rich type phase, which turns out to be disordered. There is cation disorder. The similarity of sites and bond lengths, MgO and SiO bond lengths, produces a cation disordered phase. This is very interesting. That is going to complicate a lot our work in making predictions for exoplanet super Earth relevant phases. But here we have cation disordered in these phases. Challenges, of course, in going forward in this direction, we need to understand how iron affects these phase transitions. And the main one, the first one we studied, is the B1, B2 transition in ferropericlase, in MgO or ferropericlase now. This phase transition has already been investigated experimentally in FeO. We are starting from the low iron concentration side as always. This is a great challenge. First of all, solid solution, this solid solution in the B2 phase. So the B1, B2 transition, B1 phase is low spin and insulator. The B2 phase is intermediate spin and metal. So this is the intermediate spin state here, clearly in the cesium chloride phase of ferropericlase. Unharmonicity is a really big problem here. At low temperatures, the site distorts, doesn't want to remain in the cubic. The site, iron site is not cubic, is distorted. Unstable phonons, and there is another complication here as well that can save the day for us. Essentially, is that these are metal. These phases with iron are expected to be metal at the pressures that we want to study them, and which means thermoelectronic citation is going to be significant. In that, to a certain degree, it saves the day because it stabilizes thermoelectronic excitation, stabilizes phonons. And also, the good news is that we might be able to address these metallic phases with standard functionals. For example, this is a phase boundary with DFT plus U, and this is a phase boundary PBE. The difference is 20 GPa. Which is great news for us, at least from the qualitative point of view. So this is where we are here. Opportunities. Why do I call these opportunities? Because we are publishing this software. For example, one of the first software we published was the quasi-harmonic, the QAGA software. Of course, there are other software out there. For PhonoP is one of the best known, but the difference is that this code addresses multi-configuration systems, and we can address order disorder or other kinds of problems with multi-configuration. For example, the first use of this technique was to study the IC7 to IC8 transition, where the high temperature phase is disordered. We simply see the disordered phase as an ensemble of structures which we will perform Boltzmann statistics in this collection of phases. And this has been quite successful, not only in this, but in other areas, including in this
please conclude to allow time for questions.
High pressure phases of the silicates germinate that I mentioned. It has been applied also to study hydrous defects in olivine. Our code to do thermoelasticity is really a unique code and has been published as well. If you know how to do quasi-harmonic calculations, this code is safe, well tested, and can do calculations of thermoelastic properties with materials of low symmetry. Up monoclinic, for example, these are the elastic coefficients of diopside compared to experiments. Here is a function of pressure at different temperatures, and here below is a function of temperature for several pressures. The predictions are pretty nice. Deviations above 1000 Kelvin, we suspect that has to do with unharmonicity. The code to do quasi-particle, to obtain quasi-particle properties for molecular dynamics and phonos, harmonic phonos, is also published, and I hope it will be useful to our community. Now, this is more what I'm going to talk about very briefly. It's more than an opportunity. It's really a great need that was recognized a long time ago. And that's one of what the virtual laboratory for planetary materials, the VLab, wanted to accomplish. We were funded for 4 years. And after that, we carried the research independently. But here is databases and online software running calculations. Cyber infrastructure, in short. Around 2010, the material science community decided to invest heavily. And today they own this type of infrastructure. Intellectually today, they take a great deal of credit for this combination, this cyber infrastructure for materials calculation. The materials project is the most well-known in the United States. A-Flow is also well-known. Materials project is essentially a great deal of a collection of data on materials properties obtained by first principles, mostly. Hundreds of thousands of materials have already been studied with simple techniques, the standard density function, GGA, LDA, but at zero pressure. A-Flow, it does a little bit.
Renata, we need to, we're out of time.
Okay, let me wrap up then. So these are well-known cyber infrastructure in the United States today, and Earth in Time acknowledge the need for cyber infrastructure development for many reasons. And this is something that we have been aware for a long time. So I encourage you to see the current VLab site, which still has a great deal of resources that were developed a long time ago. And we run software for predicting rock velocities in rocks. For example, the Abers and Hacker, we run this online, and we are helping to improve the materials properties behind the software. And there are several other calculations that can be done online that are still functional. But this is the type of infrastructure, automated calculations that we would like make available. That is needed. The automated calculations done in a coherent website will have information about provenance. And certainly we needed to connect with experimental databases, and will give access to much of mineral properties that we needed to understand Earth and planets. So this is a great need that has been recognized a long time ago. And now Earth in Time recognizes as well. Thank you very much. I'm sorry if I stretched it a little bit further.
Oh, that was a great talk.
Thank you very much for your attention.
You really covered a lot of material here, but unfortunately, I say that we have people lined up with questions, but I think we need to move on. Write your questions in the chat, and
Yep,
Renata,
I will try to answer in the chat as well.
Okay, thanks a lot.